Hey guys, Ms. Gosling here. In this video, you are going to learn about resistance. By the end of this video, you will be able to determine the resistance of both ohmic and non-ohmic resistors. So let's go ahead and get started. Now, ohmic resistors are what you are used to at this point. They're represented in our circuit diagrams, often by something that looks like this, or once you leave the IB program and are creating circuit diagrams in college, by a symbol that looks like this. An ohmic resistor is defined as a resistor that has a constant resistance. So what happens is if we plot voltage versus current for that resistor, we get a straight line, as you can see over here on the left side of my screen. So our ohmic resistor is going to follow the law V equals IR, and R is going to be a constant. So V versus I will, of course, be that nice straight line. Non-ohmic resistors, on the other hand, are resistors whose characteristics change as they are running in a circuit. You can see here a few examples of non-ohmic resistors. So we have the most common, which is a filament lamp or light bulb. And what happens with our filament lamp is it is going to heat up. And as it heats up, you can see its resistance is going to change. And we can see this because the relationship between V and I is changing, and we know that because we don't have a straight line. Similarly, gas discharge tubes, thermistors, thermionic diodes, and semiconducting diodes all also are non-ohmic resistors. So unlike our nice ohmic conductor, they are going to heat up over time, and as a result, will have their resistance change. Now, I will clarify. Other characteristics about a resistor can change its resistance, its resistivity, but temperature is the most common, and when you are seeing something's resistance change in a circuit, so when you see a non-ohmic resistor, it's most likely because something is going on with its temperature, and its temperature is changing as it sits in our circuit. Now, one thing I do want to clarify, non-ohmic resistors still follow Ohm's law. So I'm going to write that down because that is incredibly important information. So non-ohmic resistors still follow Ohm's law. So what this means is that regardless of whether a resistor is ohmic or non-ohmic, we know that V is equal to IR. The difference is that for a non-ohmic resistor, we can't just give a number for R. Instead, we're going to figure out R by reading our VI graph. So what you'll do is you'll go over to a given voltage. You'll see what the current is at that voltage. And by plugging in that voltage and that current from your graph, you'll be able to figure out the resistance of your non-ohmic resistor at different voltages and different currents. So again, that is going to be the key piece of information, or the key way that you're going to be solving these non-ohmic resistor problems. You'll be reading your voltage and current from the graph and using that to figure out your resistance. So what I want to do is introduce the equality of resistivity. So resistivity is a quality of quality of the materials a resistor is made out of. Or instead of resistor, I'm going to say a circuit component is made out of. Some materials are going to have a higher resistivity than others. Some materials are going to have a resistivity that changes significantly with temperature, while others won't. And so resistivity is often either the thing you are solving for in an equation or the thing or a given. So for example, you might be given the resistivity of copper wire. Now, the equation for resistivity is given below. We're going to represent resistivity with the letter rho, which looks like a curly P. It often looks a little more like what I just drew rather than this guy. And its name is rho, which is a Greek letter. Now, our resistivity is equal to our resistance, which you should recognize as this capital R. And then we have two new things. So let's say I have a copper wire like so. and I have a cross-sectional area of my wire. I'm going to represent that by the letter A. Now you may be given in a problem, for example, your diameter or your radius rather than your area, in which case you can just use the equation A equals pi r squared to solve for your cross-sectional area. Now, my wire also has a defined length, and our resistivity is going to be equal to our resistance times our cross-sectional area divided by the length of my wire. And when I change this equation around to solve for my resistance, this relationship makes a lot of sense. So we've got rho times L over A is equal to our resistance. And again, that's just solving for our capital R here. So resistivity is a quality of our wire. That's not going to change. So we're not going to worry about it. What I want to do, though, is talk about how area and length are going to affect my flow of electrons. So let's start by talking about area. And when we talk about area, what I want you to think about is a hallway. And specifically, what I want you to think about is trying to get through a crowded hallway versus a crowded hallway, one that's narrow and one that's wide. Now, I don't know about y'all, in my experience, getting through a larger hallway, a wider hallway, is much easier than trying to get through a narrow hallway because wider hallways have a lot more space, so it's easier to dodge people. Similarly, when we have a larger wire, it's easier for electrons to travel through. And so we're going to have a greater current and therefore a lower resistance. Similarly, think about whether it's easier or harder to get down a long hallway versus a short one. When you get down a long hallway, you have a lot farther to go. So it's much easier to get through a short crowded area than a long crowded area. So as the length of our wire, of our resistor, of any component in our circuit increases, the resistance of that component is also going to increase. So often when you are doing a lab or when you are solving problems, length and area are the things that you're changing, the things that you are given, and you're going to see how they're affecting your resistance, or you'll use them to figure out your resistivity if your resistance is given. So let's go ahead and talk about our takeaways. So first of all, not all resistors follow Ohm's law. So if the temperature of a resistor changes as current increases, then the resistor will be non-ohmic. So I'm going to go ahead and highlight this first sentence because that is the important part here. And then finally, we know that resistivity is directly proportional to area over length, and we know that resistivity is a quality of our material. So it's something that is kind of built into our resistors and our wires. So guys, you now know about ohmic and non-ohmic resistors, and you have learned about what resistivity is and how we can find it. So now it is your turn to give it your best shot. Best of luck and happy solving.